Hello my dear friends, yesterday we have seen elasticity. In continuation with that we are now going to see stress to strain diagram. Okay, actually it is considered as strain axis, this one is stress axis. Okay, so in this strain axis, so we can see this is nothing but it is a graph of the metallic wire, okay, which is under some stress, or we are applying a stretching force. So then what happens to that particular wire? So that is shown in this diagram, I mean ray diagram. This is the graph which shows. So here from O to A, this is the elastic region. So until this, the metallic wire, it has more elastic in nature. So after this A point, then it reaches to, this is the proportionality limit. So after that the elasticity little bit decreases and goes on like that, and then if it reaches to B, so it is the elastic limit. So after that it doesn't have any elasticity, okay, so it loses its elastic property. Then it reaches this D, where D is the fracture point. So here the metallic wire breaks. Okay, so this is the point D where the metallic wire breaks. Okay, see, actually this is nothing but this D fracture point is breaking stress, and then this B elastic limit is yield stress. So the meaning is we are applying a stress or force on the particular, or stretching force on the particular wire. Then what happens? So it extends up to the breaking stress. So after breaking, the stress cannot be applied, right? So the stress reaches, this breaking stress reaches the fracture point of a metallic wire. So until this A point, we have seen this elastic region. So this graph shows how the metallic wire and its elasticity and its property, everything. So yesterday we have seen Young's modulus. So Young's modulus is nothing but, if you consider this stretching force to the wire, which is cylindrical in nature, then what happens? A decreases and then L increases. A is the cross sectional area of the wire and L is the length of the wire. A decreases and L increases due to the stretching force. That stretching force per unit area is represented as the stress. Okay, that is the longitudinal stress. That means we are applying this force longitudinally. So it is a longitudinal stress, and then due to that some strain is developed in the body or the material. Then what happens? Deformation happens, the length stretched. Now the original length is L, it is stretched up to some delta L. Okay, some difference in length or change in length is there. So that change in length by original length is recorded as a strain developed in the material. Okay, the ratio between the longitudinal stress to the longitudinal strain is nothing but it is an Young's modulus. We have seen yesterday. So this Young's modulus is nothing but, so it is, we can see this Young's modulus only in solids. Okay, and then it is independent of any size of a material. The size doesn't matter. And then Young's modulus increases on adding impurities. If you add impurities, then Young's modulus increases. Then suppose if you hammer the material, it increases its elasticity. Okay, and then annealing decreases elasticity. What is meant by annealing? Alternate heat and cool of a material, it results in decreases of elasticity. Then it decreases with rise of temperature. If the material is brought into the rise of temperature, then Y decreases. Then if Y increases, then the material is said to be more elastic. That we know, isn't it? So hence steel is more elastic than rubber. Yesterday we have seen. So and then I must tell you about the energy of a material also. So the energy means it is the energy of a strain developed in a body, okay, in a material. So this is nothing but strain energy. Strain energy in a material is given by So it is recorded as a work done. What is the work done now? You are applying a, what is work done actually? Work done is nothing but if you apply a force, then the body gets displaced due to the force applied, right? Here, if the force is applied, then what happens? The dimension of a material is changing now. So whether it is longitudinally bulk or bulk change or tangential shear change, whatever it may be. So here the work done is nothing but average force into change in length. Okay. This average force is nothing but, yesterday we have seen what is Young's modulus. Young's modulus equal to force per unit area. This is longitudinal stress to longitudinal strain. This is strain, this is stress, right? So F by A by delta L by L. If you brought this, F by A is equal to delta L by L into Y, then you can substitute here, instead of F, you can substitute Y into this A into this delta L by L. Already delta L is here. Then this is nothing but it is work done. Okay. This is nothing but it is work done. Okay. Work done in a material of the wire, metallic wire. Then what happens? If you want to calculate the strain energy, actually you must know the stress is applied on the material externally. Okay. Strain is the energy stored, that means strain is the energy produced in the material, okay, due to the applied stress. Okay. So here strain E, strain energy is nothing but work done by area into length. So you are substituting this area and length from this. So delta L by L into delta L by L. So you will be getting half into Y into, what is this delta L by L? Strain, longitudinal strain. So strain square. Okay. So we can represent energy is equal to half into, what is this Y actually? Y is Y into strain square is given, right? So what is Y into strain square? We can substitute like this, right? Y into strain. Okay. This Y into strain is nothing but it is stress. Because Y is equal to stress by strain. Okay. So Y is equal to stress by strain. So Y into strain is equal to stress. We can replace Y into strain by stress. So we can either use this relation or this relation for energy stored in the metallic, energy strain developed in the metallic wire due to the stress applied on the metallic wire. Okay, so I'm going to give you an assignment in our Google classwork regarding this Young's modulus. Try to do this. It is very interesting also. Thank you guys.